GIS basics. In the next few minutes, we will walk through the key concepts of geographic information systems, what GIS is, and how it works, and why it's so valuable in solving real world problems. Let's begin by understanding what GIS actually is. GIS, or Geographical Information System, is a software system that helps us organize, store, analyze, and display geospatial data, meaning data that has a location component. It allows users to understand relationships, patterns, and context in data. In simple terms, GIS helps us make better decisions by connecting data with geography. For example, visualizing how resources, people, or events are distributed across a region. GIS has a wide range of real-world application. It can be used to identify underserved communities by mapping access to education, healthcare, or job opportunities. It is also essential in disaster response and management, whether tracking weather, floods, or hurricanes in real time. Urban planners use GIS for infrastructure development and zoning, while public health researchers use it to analyze disease outbreaks or environmental health risks. In short, GIS plays a key role in improving efficiency, communication, and decision making across many fields. A GIS system has four main components that work together. First, the hardware, the physical device that runs GIS software and collect data. Second, um, Second, the software programs such as ArcGIS, QGIS, MapTube, which allows us to process, analyze, and visual spatial data. Third, the data, which includes all types of geographical information systems like satellite, census records, and maps. And finally, the people, the experts who use GIS tools to interpret results and make informed decisions, such as urban planners, data analysts, and public health professionals. We will look at two main types of GIS data used to describe geographical features. The first is spatial data, which tells us where something is located on the Earth's surface. For example, the map on the left shows spatial data of spatial features like forests, rivers, and roads. The second is attribute data, which describes what those features are, including their characteristics, types, or conditions. The table on the right is an example of attribute data showing details like rock type, dispositional environment for each location. Together, spatial and attribute data allow us to fully understand both the location and characteristics of geographical features. Have you ever wondered how GIS represents the physical world around us? Spatial data forms foundation by GIS by capturing the physical location and geometry of features on the Earth. These can include natural formations like rivers and mountains, or man-made structures like roads and buildings. GIS simplifies these complex structures features into points, lines, and polygons for analysis. Points mark for specific locations, lines depict linear features, and polygons represent defined areas. Understanding spatial data is crucial because it enables researchers and analysts to visualize real world relationships accurately. Spatial data is categorized into two primary types, vector data and raster data. Vector data uses points, lines, and polygons to represent discrete features such as customers, roads, or land parcels. On the other hand, raster data is composed of grid of pixels where each cell holds a value of representing continuous data like elevation, land usage, and satellite imagery. Together, these data models help create detailed and layered geographic information systems, or GIS, which support informed decision making across a wide range of industries. After knowing what these are, the next question is, what are they saying? Where is this where attribute data becomes essential? Attribute data describes the non-spatial characteristics of geographic features such as name, type, function, or of a location. For instance, a school on a map is represented spatially as a point, but attributes might include the number of students or institution type. In GIS, attribute data gives meaning to spatial data, turning simple coordinates into meaningful contextual information used for decision making and research. Examples of attribute data for three types of spatial features: points, lines, and polygons. At the top, we have point data, which represents specific locations such as trees or sampling sites. Each point has attribute data like plot size, type, and vegetation class. In the middle section we see line data, which is used to represent linear features like roads or trails. The attributes here describe details of such a type of road, its status, and maintenance schedule. Finally, at the bottom, we have polygon data, which defines areas such as grasslands, forests, and social associated attributes include the type of vegetation, its classification, and protection status. Together, these examples illustrate how attribute data adds descriptive meaning to spatial features in a GIS, explaining not just where something is, but where it represents. Data sources. Where does all the data used in GIS come from? GIS relies on a variety of data sources to ensure accuracy and depth. These include publicly available datasets from government agencies, universities, and NGOs. Commercial data providers offer specialized data sets for industry-specific needs. Crowdsourced data like OpenStreetMap relies on community contributions. Additionally, field data collected using GPS devices and remote sensing data from satellites or drones add real-time and high-resolution insights. The diversity of data allows a GIS to be used across fields like transportation, health, and environmental management. Before conducting any GIS analysis, it is vital to evaluate data quality and relevance. We must ask, how accurate and appropriate is the data of our study? Data quality refers to its precision, completeness, and reliability. Data accuracy measures how closely the dataset matches real-world features, while data scale determines the level of detail. Data relevance ensures that the data aligns with the goals of a project. Understanding these considerations helps minimize errors and ensures that GIS analysis produces meaningful and dependable results. This slide shows how raw geographical data is transformed into meaningful map analysis using GIS software like ArcGIS Pro. We started with geographical environment, which includes all natural and built features such as rivers, vegetation, and infrastructure. Data from ground surveys, census records, and remote sensing is collected and compiled into GIS as recognized geographical information. Next, the data is refined through selection, classification, simplification, and symbolization. These steps organize the data and prepare for visualization. Using GIS tools, features are styled in with symbology, applying specific colors, line types, styles, and symbols to represent different categories like land cover or transportation. Labeling and annotations is then added to display key information such as names, zip codes, or elevation. Analytical tools like buffering, overlay, and spatial statistics are applied to uncover patterns and relationships in data. Finally, all of these elements combine to create a map image, a clear, well-designed visual that allows for reading, analysis, and interpretation. Through this process, GIS turns raw data into powerfully color-coded maps and that help visualization and inform decision making. Vector data format. How do we store and organize spatial data efficiently? The vector data format provides one of the most common structures in GIS. It represents real world features using points, lines, and polygons. Each feature is organized with a feature class. Groups of geometries sharing similar properties, layers in GIS display that datasets visually, allowing users to manage and analyze them efficiently. This structured approach supports detailed mapping and spatial modeling and advanced analysis across various disciplines. Let us now explore how Esri's ArcGIS handles explore data, vector data. In ArcGIS, Um, vector data can be stored as shapefiles or geodatabases. A shapefile consists of several files that work together to define geographic features and their attributes, such as a .shp, .shx, and .dbf files. A geodatabase, however, is more advanced format that stores multiple types of geographical data sets within a unified structure. It offers better data integrity, scalability, and management, for which are crucial for professional and academic GIS applications. At this point, it is important to ask which tools make all this possible. GIS software provides the environment to visualize, analyze, and manage spatial data. Popular tools include ArcGIS by Esri, QGIS, MapInfo, and Google Earth Pro. These platforms offer advanced functionalities such as map editing, spatial analysis, and remote sensing integration. GIS software is used extensively across disciplines from urban development and environmental planning to logistics and healthcare, enhancing research and decision making through spatial intelligence. ArcGIS Online is a powerful web platform developed by Esri that enables users to create, share, and analyze spatial data collaboratively. It's, it supports real time data visualization and allows users to publish interactive maps with its integration capabilities and analytic tools. Our ArcGIS Online is widely used for data driven decision making, project management, and geospatial collaboration among organizations and researchers. This slide shows the map visualization we created in ArcGIS Pro and as a part of our project completed a few weeks ago. Here, we analyzed underserved communities across Texas using zip code level data. The map displays various socioeconomic indicators such as unemployment rate, education level, labor force participation, and poverty exchange. Each symbol represents a zip code, and the color-coded symbology helps us easily compare different factors. For instance, red indicates higher employment or poverty, while green highlights areas with stronger labor force participation. By combining attribute data with spatial mapping, ArcGIS Pro allows us to visualize real-world disparities, identify regional patterns, and support data-driven decision-making. This slide shows a real-life visualization project created in ArcGIS Pro. Here, we mapped and digitized various buildings across University of Texas at Arlington campus. Using the feature tool, we defined a new polygon layer named buildings and manually traced the outlines of key structures such as Science Hall and Institute for Instability. Each building was stored as a separate feature with attributes like name and area, allowing us to analyze and visualize the spatial layout of the campus. This exercise demonstrates how GIS can be used for precise building mapping, feature labeling, and spatial organization within a real-world environment. Finally, let's look at an open source alternative to ArcGIS. QGIS is widely used free um, platform that supports powerful spatial mapping and data management. It offers extensive plugin support and compatibility with numerous data formats, making it highly flexible for researchers and professionals. Its accessibility makes it an excellent choice for academic environments, allowing students and organizations to perform comprehensive GIS analysis without licensing costs. So this is the QGIS polygon mapping of UT Arlington. So some data and resources that are offered are ArcGIS series, ArcGIS Online, Living Atlas, OpenStreetMap, and Natural Earth. And some popular data sets that are used for this project are USGS, Census Bureau slash Tiger, and State Government GIS Hub. Some learning resources are Esri Academy, GIS Fundamental, GIS Basics by Esri, Coursera, Fundamentals by GIS by Eric Howard, Esri Documentation, QGIS Documentation, and Textbook Introduction to Geographic Information Systems by him. That's the end of our presentation. Thank you so much for listening.